Alright, so the goal of this video is to show that the stable stems are finite, so that pi I stable is finite. And this is for I greater than 0. Of course, we know that when I is equal to 0, we should just get a copy of the integers, so that's not finite. And some good references here are Hatcher's spectral sequences and also Mosier and Tangora. So let me just remind you, since we stepped away from this for a while, that pi I stable just means we look at pi n plus I of Sn, and the whole idea is that this stabilizes for large n, and in particular, if we take n greater than I plus 1, then our Freudenthal suspension theorem tells us we have an isomorphism, and so those end up being all the same. Okay, so that's our stable value that we're interested in. And as I said, pi 0 stable, of course, we know is the integers. That's just pi n of Sn. That's always true. We don't even really need to go to the stable range for that one. And we showed in lecture 29, I believe, that pi 1 stable is a copy of Z mod 2, and it's generated by the Hopf map, right? And notice, by the way, that is finite. So, okay, that's a good sign, good sanity check. This is a reasonable thing to hope might be true. And in fact, I claim it is true, and we'll use a lot of Sarah's work to prove this. So I don't think Sarah called it this, but I'll define a Sarah class. Sometimes this is just called a class of abelian groups. I'll denote it C. This is just a collection of abelian groups that satisfy some properties. Oops. And definitions will vary here. So the definition I'm going to write down is not precisely in either of these resources, but is sort of implicitly in there. So the first thing that we want, and I think they all agree on this one, is that for any short exact sequence of abelian groups, A goes to B goes to C, then B is in our class if and only if A and C are in the class. Okay, so I lost my note about that, but the point is that means that this is closed under taking quotients, subgroups, stuff like that, okay? And the second thing is that if you had two abelian groups in your class, then if you take the tensor product, that's also going to be in the class. And in fact, because we need Tor when we're computing things like homology or cohomology, we might also want the higher derived tensor products to be in the class. So we'll just make that part of the definition. And the last thing is that if you take something in your Serre class, then if you look at the homology of an Eilenberg-MacLane space, say Ka1, where A was something in your class, then this homology group is also in that class, and that's for all n greater than 0. Whew, okay, struggling to write. So again, definitions vary here, but these are all sort of the properties we're going to want for the classes we'll be interested in. So we might as well just take that as our definition. Okay, so we've got this nice class of abelian groups, and some good examples to have in mind are we could just take C to be the class of finitely generated abelian groups. Okay, I won't prove any of these, so exercise is to check that these examples are really examples. Another one we could take is torsion abelian groups. Some of these are basically trivial and some of them take a little bit of work to prove. So I think most of this one is trivial, and then it's maybe a little bit more work to prove 3. We could instead take C to be, well, torsion abelian groups, but with another property. So specifically, we might want our elements to all be divisible by primes in some fixed set of primes. So I'll just say divisible by a fixed set of primes. Of course, it doesn't make sense to be divisible by a set, but I just mean divisible by all the primes in our set, okay? And then another example is we could take finite things in that previous class, and that's also going to work. Or we could take finite torsion abelian groups with, this is really a special case of the one above. So I'm going to say the order of every element relatively prime to some fixed prime p. Okay, so that's just taking, in the previous one, the set of primes to be all the other primes beside my favorite prime p, and then taking the finite things in that class. Okay, so now it looks like, well, you could just willy-nilly take any sort of class of abelian groups, and that's not quite true. So as a good sanity check, this is actually a little bit restrictive. A non-example is if we take C to be all torsion-free abelian groups. Okay, and really this easily breaks down from our quotient property, so we get this short exact sequence, say z to z via times 2 to z mod 2, and of course this middle thing is torsion free and abelian, but this last thing is not, even though the first thing is. Okay, so this doesn't satisfy that first if and only if, right? Our middle thing is in our class if and only if the two outer things in the short exact sequence are also in the class. Okay, great. So we're going to use these Serre classes to, well, obviously one of them is going to be things that look like finite abelian groups. So those are our finite torsion abelian groups. And we're going to want to show that the stable stems satisfy that they live in this class. So how are we going to do that? Well, we're going to use first this theorem that says that if X is simply connected, then its homotopy group, so pi I of X, is in some class for all I, if and only if the homology groups of X, and now I'm not writing with integral coefficients, but that means with integral coefficients, if those are also in this class for all I greater than 0. Okay, first let me point out, of course I don't want to include I equals 0, that'd be silly because as long as this thing is simply connected, that's always going to be a copy of the integers, and I might want things like torsion abelian groups, okay? But we'll just include I greater than 0. That makes more sense. And let me point out, this is really all we're going to need, but it's maybe nice to know that this also holds a little bit more generally. So you really just need X to be path connected. And you also need, the main thing we were getting from the simply connected is that pi 1 acts trivially on the higher homotopy groups. And that's in the simply connected case just because, of course, it is trivial. So I just want pi 1 to act trivially on pi I of x for all I greater than or equal to 1. And otherwise, if we didn't have that restriction, maybe a good exercise is to check that RP2 would be a counterexample. For some choice of Serre class C, and I'll leave that to you as a good exercise. But notice that as an immediate corollary, we find out that pi I of Sn, well, I just want to choose some appropriate Serre class, and maybe, well, I certainly don't know everything about the homotopy groups of Sn, right? If we did, we'd have this problem of the stable homotopy groups solved and we'd be done. But I do know everything about the homology of Sn. That part's not so bad. And I can't say that that's always torsion or, torsion with elements being relatively prime to some other prime or something like that, because of course Hn of Sn is Z. But I can say that it's finitely generated. Of course, abelian. So that's kind of nice. I already know that this is finitely generated, and I don't have to worry about anything too crazy, any copies of Q, for example. And of course, that's only true for n greater than 1 coming from this result. Okay, just because I want it to be simply connected. Great. So now let's move on to our main theorem and talk about how we'll prove it. So our claim is that the stable homotopy groups pi I stable are finite for I greater than 0. And the strategy of our proof is maybe a little bit odd up front. So really, maybe I should have said a little bit strange, but we're going to show for n odd, so it really will be odd up front, that we look at pi I of Sn. And now notice that's not pi I stable, right? I should be looking at pi n plus I, but I'm not going to worry too much about it since the claim is that all of them are finite. This will do. What we'll do is show that this is finite for all I greater than n. Okay, I sort of mixed up two things there. So what I'm trying to say is that I'm not indexing here n plus I, and that's not such a big deal because I'm going to take the stable thing, so that will be fine. And but I didn't address, why n being odd is enough. Really, I want this to be true always, but of course the Freudenthal suspension theorem tells us that this value stabilizes for large I, or sorry, for large n and large I guess. Well, maybe small I relative to n. Okay, I'm tripping up my words. My point is that this stabilizes, and so it doesn't matter that this n we chose was odd. We'll get the same thing for the next thing where n is even. We just suspend in both the I and n. Okay, so pi I stable will be finite for all I greater than 0. Okay? All right, hopefully that made sense. I think I tripped up a little bit what I was saying there, but the point is it's enough to show this works for odd spheres and that all their higher homotopy groups are finite, and then the Freudenthal suspension theorem will give us all our stable stems are finite. Okay, so now let's just fix some n odd, and to make sure this thing is simply connected, let's fix n greater than 1. I guess I could have said, well, that's fine. Okay, and what I want to do is use the same technique we saw before. So I'm going to look at this map F from Sn to Kzn, which I could think of as inclusion of the bottom cell, or however I want to think of it, but such that as we chased through in lecture 29, I think there n was 3, but I want this to induce my isomorphism from pi n of Sn to pi n of Kzn. And that was like through the Hurewicz map and realizing the fact that Kzn was representing cohomology, right? So I want this to be an isomorphism. Maybe there are, well, okay, so just as we did in lecture 29. Okay, and then again, just as we did there, we're going to convert this F to a fibration. And I'll use notation a little bit and just care about the homotopy type. So it has some fiber, and then I've got this fibration. Okay, so this isn't really F, but it's some approximation to F, right? Okay, and that fibration gives me a long exact sequence in homotopy. So what does that tell me? Well, it's essentially the same sort of thing that we found last time. So we'll learn that pi I of x is, well, most of the time it's the same as pi I of Sn, right? This Kzn only contributes one homotopy group and it's in degree n. So that will match with my Sn at that spot. And then everywhere else, this will be 0 in the long exact sequence, and so these will match. Okay, so it's pi I of Sn whenever I is greater than n, and it actually agrees when I is less than n as well, but that means it's just 0. So this is 0 for I less than n, and using that Kzn to peel off that homotopy group in degree n says actually 0 for I less than or equal to n. Okay, so I think this is worth writing down because this is a technique we'll use again. So the idea is we used Kzn to strip off the nth homotopy group here. Okay, so just worth emphasizing that that's a convenient technique. All right, great. So what I really want, though, is to continue this fiber sequence backwards. So just as we did in the last time, we can convert x to Sn to a fibration, or we can just think of extending the pupa sequence. So let's take our x to Sn and convert this to a fibration. And then there are a few ways. I'll leave this as an exercise, following the same techniques we used last time, to see that the fiber here has homotopy type Kzn-1. Okay, so we've just extended our pupa sequence back. Great. Okay, and now it seems like what are we even doing, right? We're supposed to be talking about Sn. Well, now I have the fibration that I want, and we're going to use the Serre spectral sequence. So maybe let me say, oops. Now use the Serre spectral sequence, and we'll do this in rational coefficients. Okay, so what does that look like? Well, this is the fibration we want to take, so we'll have E2, I guess PQ, is going to be, well, it should be the cohomology of the base with coefficients in the cohomology of the fiber. Notice I'm working with coefficients in a field, so I can just take the tensor product on that E2 page and think of this as a spectral sequence of algebras. So let's go ahead and do that. So that's HP of Sn in rational coefficients. Tensor HQ of the fiber was Kzn-1 in rational coefficients. And then this converges to HP plus Q of the middle thing, the total space in rational coefficients. Okay, now remember that a long time ago we had the exercise, and if you didn't do it then, you should do it now. Just pause the video. That if you want the cohomology of kzn in rational coefficients, it's not too bad. So there's just two cases. You either get polynomial in some generator or exterior in some generator, and it's really just depending on the degree. So this is when n is even, and we get exterior when n is odd, and in both cases, the degree of x is n. Okay, so now I'm finally going to use the fact that I'm assuming Sn was an odd dimensional sphere, right? So our n was odd. So that tells me n minus 1 is even, and I get to deal with this polynomial thing. Great. Okay, so let's run that Serre spectral sequence. On our E2 page, what does that look like? Try to leave myself enough space here, though somehow I never do. Okay, but let's try. So, of course, I have 1 tensor 1 in degree 0. I'll just write that as 1. And then on the p-axis, I should put the cohomology of the base in rational coefficients. So that's just a q in degree 0 and a q in degree n, and maybe let's call that generator y, just because we named the other thing x. Okay, and then when I look at the cohomology of the fiber, along the q-axis, I've got things only concentrated in certain degrees, right? I've got this thing is polynomial, so I have x squared, and I'm just writing whatever degrees they end up in. X cubed, so on. Okay, great. So, this thing is the tensor product, so that tells me actually I have q x tensor y, I've got a q for x squared. Tensor y, I was trying not to write the tensor, but then saying it made me want to write it. I've got a copy of q for x cubed tensor y, and so on forever. But a bunch of zeros here, and here, and here, and here, of course, and everything out here is 0. Okay, great. So now we need to remember that actually the homotopy of our total space, the thing that we should be converging to, we know that this basically has homotopy just like Sn, except we've peeled off one more homotopy group, so it has nothing in degree n. So the point of that is that x is n connected. Okay, so here I wrote down the cohomology of the base. And here I wrote down the cohomology of the fiber. I think you guys probably don't need these reminders anymore, but I don't know, maybe it's been a while. Not that you can even read that one. Okay, and then this should be converging to the cohomology of the total space, which was our x. And that thing had the same homotopy groups as Sn, except that nth one was pulled off, so that's n connected. Okay, so that tells me that I should have an isomorphism here, because otherwise I'd end up with something, well, okay, it tells me I should have an injection here, right, because otherwise I'd end up with something in degree n minus 1. Since this thing will have total degree n minus 1. And any injection from Q to Q is an isomorphism, it's a map of fields. Okay, so that's an isomorphism. And then up to renaming, I could say that tells me that dn of x is equal to y, right? So that tells me, okay, maybe I should have just written that explicitly. So let's say that tells me that dn is an iso, going from the n minus thing in the n minus 1 thing in the fiber to the n thing in the base, and so then up to relabeling the generator, so we could call that dn of x is y. And then our Leibniz rule tells us dn of x squared is 2x dn of x, just using the derivative rule, right? And so that's 2xy, and in fact, dn of x to the m is mx to the m minus 1 dn of x, and that's just mx to the m minus 1, oops, times y. Okay, so we're working rationally, so those are all a bunch of isomorphisms. So that's an isomorphism, that's an isomorphism, and so on. Okay, great. So one of the best kinds of spectral sequences, everything dies, and that tells us that the reduced cohomology, of course we've still got this q in degree 1, or degree 0, sorry, but that tells me that the reduced cohomology of x with rational coefficients is 0. Great, no extension problems to solve, nothing complicated there. Of course, over Q, all the extension problems would have been easy anyway as vector spaces. Okay, and now maybe at this point you're like, wait, we're supposed to be learning something about Sn, right? So how do we get back there? Well, what I really want to find out is about the cohomology of x with integral coefficients. And I do that by saying, well, if you wanted rational coefficients, you just take the integral coefficients and tensor with q, right? There's no Tor term. And this is always 0. So that tells me that there would, well, maybe let's just do reduced. Why not? Okay, so that tells me that the reduced cohomology of x in integral coefficients is finite. And how does that help me? Well, remember that we had this theorem that if we knew the homology groups were in some Serre class, then we knew the homotopy groups were in that Serre class. So finally, our mod C theorem, which was really just the thing that I said, right? Our X is simply connected. Its homology groups all live in the Serre class that we have finite abelian groups. And so that's going to tell me that the homotopy groups are also finite abelian groups. Okay, that's where I just take the finite torsion abelian groups. I guess I should have said that as an example at the start. Silly to have left that one off. Okay. I sort of implicitly had it in there, but I should have said it explicitly. Sorry about that. Okay, so the upshot is the homotopy groups of this thing are finite, but this thing, remember, was an approximation to Sn. So our homotopy groups of X are the same as the homotopy groups of Sn as long as we're above degree n. Okay, and then that tells us that the homotopy groups of Sn are finite. Now remember, n here was this was an odd dimensional sphere. N was odd. And then our Freudenthal suspension theorem finishes it off and tells us, oh, well, that stabilizes. So if you suspended in both coordinates, you'd be talking about an even dimensional sphere, but you haven't changed what stable stem you're talking about, right? And so all of our stable stems are finite, well, only when we're looking at I greater than 0, right? Of course, pi n of Sn is not finite, but that completes the proof. Okay, so I think that's neat. This really made use of these Serre classes, which we hadn't introduced before. And essentially, after that, the proof is just the Serre spectral sequence. So now we know that all the stable stems are finite. We know pi 1 is z mod 2. And we know pi 2 is, well, some finite abelian group. And we know it was a finitely generated abelian group. Right now we know that it's torsion. And so we just need to figure out sort of prime at a time what kind of divisors we have there. All right, let me stop there.